There is a boundary around everything humanity has ever seen. It is not a wall, it is not the edge of space. There is no sign posted at the limit, no abrupt darkness where the universe stops. The boundary exists because light has had only a finite amount of time to reach us. Beyond it, there may be more galaxies, more matter, and more history. Possibly far more. But no signal from those regions has arrived here, and depending on how the universe evolves, some of it never will. That distinction is easy to miss. The observable universe is often spoken of as though it were the universe itself. It is not. It is the region of reality from which information has been able to reach our location since the early cosmos became transparent. The difference between those two ideas changes the question completely. We do not know how large the entire universe is. We do not know whether it is finite or infinite. We do not know whether the region visible from Earth is typical of the whole. We can infer, we can test models against what reaches us. But the largest object science attempts to describe may extend beyond every possible observation. And the limit is not simply a matter of building a larger telescope. No instrument can collect light that has not had time to arrive. The universe is about 13.8 billion years old, so it might seem that the farthest observable matter should now be 13.8 billion light-years away. That would be true in a static cosmos. But space has been expanding while the light was traveling. A photon may spend billions of years crossing a distance that continues to grow beneath it. The galaxy that emitted the light does not remain where it was when the journey began. By the time the signal reaches us, the source may be much farther away than the simple light travel time suggests. This is why the observable universe has a present-day radius of roughly 46 billion light-years. Its diameter is close to 93 billion light-years. That number does not mean light has moved faster than light. It means the distance between widely separated regions increased while the light was already in transit. Relativity limits how quickly objects move locally through space. It does not require the expansion of space itself to behave like an ordinary object crossing a fixed background. The result is a horizon defined by history. Every observer has one. An intelligent species in a galaxy billions of light-years away would not see our observable universe. It would see its own, centered on itself. Some of its visible region would overlap with ours. Some would not. There may be galaxies whose ancient light can reach that civilization, but can never reach Earth, and galaxies visible to us that remain permanently absent from its sky. No location is the center of the entire universe, but every observer stands at the center of an observable sphere. That sounds like a reassuring symmetry, until its consequence becomes clear. Reality may contain regions that are not merely difficult to reach. They may be impossible for us to detect, even in principle. The most distant light we directly observe does not come from the first instant of the universe. It comes from a later period, hundreds of thousands of years after the beginning, when the cosmos cooled enough for electrons and atomic nuclei to combine. Before that transition, matter and radiation interacted so frequently that light could not travel freely across large distances. The radiation released when the universe became transparent still surrounds us. It has been stretched by expansion into microwaves, forming the cosmic microwave background. When telescopes map that radiation, they are not photographing a physical shell at the edge of existence. They are looking back toward a surface in time, the earliest layer of electromagnetic information that can travel to us without being repeatedly scattered. There was a universe before that light was released. We know this because the later universe carries evidence of earlier conditions. The abundance of light elements, the expansion of space, and the structure preserved in the microwave background all point toward a much hotter, denser phase. But ordinary light cannot show it to us directly. Already, the visible cause contains a hidden past. Beyond the cosmic horizon, it may also contain a hidden exterior. Those two limits are different. One blocks our view because the early universe was opaque. The other blocks it because the signal has not reached us. Yet both reveal the problem. Observation is not a window opened onto all reality. It is a narrow record shaped by the behavior of matter, the age of the cosmos, and the geometry of space-time. We often picture astronomy as a steady expansion of knowledge. Larger mirrors reveal fainter galaxies. More sensitive detectors uncover weaker signals. A new wavelength opens a part of the sky that had been invisible. That pattern is real. But it can create the impression that every unknown is temporary. The cosmic horizon is not temporary in that sense. As time passes, light from some currently unseen regions may enter our view, but cosmic expansion complicates the picture. The expansion is accelerating, and there are distant regions whose light emitted now will never reach us. They are not moving through space than a local beam of light. The space between us is growing in a way that prevents the signal from ever closing the distance. We may still see those regions as they were in the remote past. Their older light began traveling toward us when the universe was smaller. But their later history can become permanently inaccessible. A galaxy can remain visible while its present has already been lost. This creates a peculiar form of knowledge. We can observe an object that still exists, study its ancient structure, measure its old light, and yet have no possible way to learn what is happening there now. The image continues to arrive long after causal contact has become impossible. The sky is therefore not a picture of one cosmic moment. It is a layered archive. Nearby objects appear relatively recent. Distant galaxies appear younger. The most remote visible matter is shown in conditions that no longer exist around us. And somewhere beyond the last information we can receive, the universe may continue, without any obligation, to reveal how far. The observable universe is enormous. It contains hundreds of billions of galaxies by many estimates, each separated by distances that resist ordinary intuition. Yet it may still be only a small patch of a larger structure, or it may be one finite region within something infinite. Both possibilities fit comfortably inside the evidence we currently possess. That is the first uncomfortable boundary. Science can describe the observable universe with remarkable precision, but precision inside the horizon does not tell us how much lies outside it. Before asking what exists beyond the observable universe, we have to confront a more basic problem. How could we ever know? The first answer is that we do not observe beyond the horizon directly. We observe the horizon itself, and then ask what kind of universe could have produced what we see inside it. That method is less satisfying than a photograph, but it is not guesswork. Cosmology works by identifying patterns that should change if the larger universe has a different shape, composition, or history. The evidence arrives indirectly, encoded in geometry, temperature, and structure. One of the most important clues is uniformity. Look in opposite directions across the sky, and the cosmic microwave background has nearly the same average temperature. The differences are real, but they are tiny. Those small variations later became the seeds of galaxies, clusters, and the large-scale structure around us. The broad similarity is harder to explain. Regions on opposite sides of the observable universe are so widely separated that, under a simple expansion history, they should not have had enough time to exchange light or heat before the microwave background was released. Yet they appear to have begun in almost the same thermal state. Two distant regions look coordinated, even though they should not have been able to coordinate. This is the horizon problem. The leading explanation is cosmic inflation, a brief period of extremely rapid expansion in the early universe. In that picture, regions now separated by enormous distances were once close enough to interact. Inflation then stretched them apart, carrying their shared conditions across a region far larger than the patch we can currently observe. If inflation occurred, the visible universe may be comparable to one small section of a landscape whose full extent is hidden. The analogy has limits. But imagine standing in a field so flat that the ground appears level in every direction. That local flatness does not tell you whether the entire surface continues forever, closes into a sphere, or bends somewhere beyond sight. It tells you only that, across the area available for measurement, the curvature is small. The universe presents a similar problem. Measurements of the cosmic microwave background and large-scale structure indicate that space is very close to geometrically flat on observable scales. Parallel lines remain parallel in the relevant cosmological sense. Large triangles behave almost as they would in ordinary Euclidean geometry, but near flatness is not the same as infinite size. A sufficiently large curved universe could appear flat within the portion we can inspect, just as a small section of Earth appears flat from the ground. The full universe could be finite and much larger than our horizon, or it could extend without limit. Current observations do not force a choice. This is where the language of cosmology can become deceptive. Scientists may describe the universe as flat, but that statement concerns measured curvature, not necessarily total extent. Geometry and size are related, but they are not identical. A flat universe could be infinite. It could also be finite if space has a more complicated topology, wrapping around itself in a way that preserves local flatness. In such a universe, traveling far enough in one direction might eventually return an object to its starting region without encountering an edge. Light could also circle through space, producing repeated images of the same galaxy or duplicated patterns in the microwave background. Researchers have searched for those repetitions. So far, no convincing pattern has established that space wraps around on a scale smaller than the observable universe. That absence rules out some compact shapes and some sizes. It does not show that the universe is infinite. It means that, if space closes on itself in certain simple ways, the repeating scale is probably larger than the region we can examine. The failure to find an edge does not distinguish between no edge and an edge too distant to matter. Cosmology, therefore, depends on an assumption that is powerful, precisely because it can be tested everywhere. The cosmological principle says that, on sufficiently large scales, the universe is homogeneous and isotropic. In plain terms, no location is fundamentally special, and no direction reveals a unique cosmic arrangement. Within the observable universe, this works well. Galaxies gather into filaments and clusters, with enormous empty regions between them. Locally, the universe is uneven, but average over enough space, and those differences become part of a broader statistical pattern. We then extend that pattern beyond the horizon. The extension is reasonable. It is supported by everything visible, but it remains an extension. There could be regions beyond our horizon with different densities, different structures, or conditions shaped by processes we cannot detect. Some inflationary models even allow a far larger reality divided into domains with different physical outcomes. That possibility is often described through the idea of a multiverse, though the word can conceal several distinct proposals. Some versions arise from inflation. Others emerge from interpretations of quantum mechanics or theories with many possible vacuum states. None of them is a direct observation of other universes. The safer statement is narrower. Certain models that explain features of our observable universe may also imply regions beyond it that differ from our own. Whether those regions should be called separate universes is partly a question of definition and partly a question of whether any connection between them could ever leave evidence here. That last part matters. A model can be mathematically consistent and still become difficult to test if its most distinctive consequences lie beyond all possible measurement. Science does not require every object to be seen directly. Black holes were inferred before they were imaged. Neutrinos were proposed before detectors recorded them. But successful inferences must affect what can be observed. The question is not whether hidden reality is allowed. The question is whether it leaves a trace. Some researchers have considered whether interactions with another cosmic region could have marked the microwave background. Others have searched for unusual large-scale features that might challenge the assumption that our visible patch is typical. There are anomalies in cosmological data, but none has established a view beyond the horizon. Apparent patterns can emerge from statistical chance, foreground contamination, instrument limits, or the difficulty of drawing conclusions from a single observable universe. That final limitation is easy to underestimate. In most sciences, repeated experiments separate reliable patterns from accidents. Cosmology has only one universe available for observation, and only one location within it. We cannot move billions of light years away to compare the sky from another position. We cannot rerun cosmic history under different initial conditions. We measure one realization. Even when the instruments are precise, the sample itself may be limited. This creates cosmic variance, an unavoidable uncertainty that does not disappear with better engineering. Some properties of the largest structures can never be measured with arbitrary precision because only a small number of those structures fit inside the observable universe. The largest possible experiment has already been constrained by the size of the laboratory. So, our picture of the universe beyond the horizon rests on a chain of reasoning. The visible region appears statistically uniform. Its geometry is close to flat. Inflation offers a mechanism that can produce a much larger domain. No repeated pattern has revealed a nearby wraparound structure. No confirmed anomaly has exposed an external region. Taken together, the evidence permits a universe much larger than the observable one. It may even favor that expectation, but it does not tell us where the larger structure ends, whether it ends, or whether conditions remain the same beyond every reachable boundary. We have learned to infer an exterior from the shape of the interior. The problem is that several radically different exteriors can cast nearly the same shadow. The obvious response is to wait. If some regions are invisible only because their light has not reached us yet, then time should solve the problem. Future telescopes will look deeper. More ancient photons will arrive. The observable universe will grow. That is partly true. The boundary, defined by everything that has had time to influence us, is called the particle horizon. As the universe ages, signals from slightly more distant regions can enter it. In that limited sense, the visible domain expands. But another boundary changes what waiting can accomplish. The cosmic event horizon marks the greatest distance from which a signal emitted now could ever reach us, even given unlimited future time. Beyond it, the expansion of space prevents new information from completing the journey. This is not the same as the edge of the observable universe. It is not the same as the distance where recession exceeds the speed of light. And it is not a physical surface surrounding Earth. It is a boundary in causality. A galaxy can be visible to us today because we are receiving light emitted billions of years ago, while the galaxy's current condition lies beyond any possibility of future contact. We see its past after its future has become inaccessible. That distinction creates a result that feels backward. More time does not necessarily reveal more of what exists now. In an accelerating universe, waiting can mean losing access. The distant galaxy does not suddenly vanish. Its light becomes increasingly redshifted as expansion stretches each wave. The signal weakens. Events there appear to slow. New information arrives with less energy and at longer intervals. Eventually, its light is shifted so far and diluted so severely that no practical instrument could recover it. The disappearance is gradual, but the causal separation is permanent. This means the night sky is not only an archive of the past, it is an archive that is being sealed. Gravity complicates the picture locally. Galaxies bound together strongly enough do not participate in cosmic expansion in the same way as widely separated regions. The Milky Way, Andromeda, and the other members of the local group remain tied by gravity. Their future belongs to a shared island of matter. more distant groups and clusters do not. Over immense spans of time, accelerated expansion will carry them beyond effective observation. Their ancient light will fade from the sky. Future observers inside the merged remains of our local galaxies may see a cosmos containing almost no external evidence that other galaxies ever existed. They could measure stars, they could study gravity. They might infer that their local system has a history. But some of the strongest evidence for an expanding universe would be gone. The cosmic microwave background would also continue to stretch. Its photons would lose energy until their wavelengths became extraordinarily long, eventually blending with other physical limits and local noise. A civilization rising late enough could inherit a universe that appears isolated and largely empty. Its scientists might construct elegant theories from the evidence available to them. Those theories could be internally careful as multiple and observationally successful. They could also miss the history that our instruments can still detect. The universe does not guarantee that every era contains enough evidence to reconstruct what happened. We happen to exist during a period when distant galaxies are visible. The microwave background remains measurable, and the expansion history can be tested through several independent methods. That does not make our period privileged in any physical sense. It makes it temporarily informative. The difference matters, because cosmology is often treated as though improved technology must eventually converge on a complete description. Technology can reduce many limits. It can detect fainter light, measure smaller variations, and distinguish signals that once appeared indistinguishable. It cannot reverse the expansion history. It cannot retrieve photons that were never directed toward our region. It cannot receive a message from a place that no longer shares a causal future with us. Some ignorance is technical. Some ignorance is built into space-time. That is where the idea of an entire universe begins to separate from the methods used to study it. We can define the observable universe operationally. It is tied to signals, distances, and the finite age of the cosmos. The whole universe is a different kind of object. It includes whatever exists beyond every current horizon, whether or not those regions can influence us. Calling all of that one universe assumes a kind of continuity. Perhaps the same space-time extends beyond our observable region. Perhaps the same laws apply there. Perhaps density and structure remain statistically similar across scales far larger than we can see. Those are sensible extrapolations. They are also not direct measurements. The situation becomes more difficult when inflation enters the argument. Inflation was proposed to explain several features of the observable cosmos, including its large-scale uniformity and near-flat geometry. In many models, inflation does not merely enlarge a pre-existing region. It stretches a tiny domain by an enormous factor, leaving the patch we can see as a small fraction of the resulting space. Depending on the model, the total inflated region may exceed our observable domain by an almost inconceivable amount. But the exact scale is not fixed by the basic idea alone. Inflation must last long enough to solve the problems it was designed to address. It could have lasted longer, possibly much longer. The observable universe does not preserve a clear measurement of the total duration. That missing duration is not a minor parameter. It determines how much reality may lie outside our horizon. A few additional intervals of exponential expansion can produce a region vastly larger than the one required to contain everything we observe. Once exponential growth begins, ordinary intuition fails quickly. Each interval multiplies the scale again. The difference between a universe only somewhat larger than our horizon and one unimaginably larger may depend on a phase whose earliest portion no recoverable trace inside our patch. Inflation can therefore explain why the universe appears smooth, while also making the full universe harder to reconstruct. The mechanism that accounts for visible order may have erased evidence of the larger structure that produced it. Some versions go further. Inflation may end in one region while continuing elsewhere, generating separate domains with histories that no longer meet. Within each domain, conditions could settle into different states. This is one route toward eternal inflation. It is not an established observation of other universes. It is a consequence that appears in some theoretical models, and its scientific status depends on whether those models produce testable effects within our own observable region. The distinction cannot be blurred. A theory may imply inaccessible domains without giving us a reliable way to confirm their existence. That does not make the mathematics meaningless, and it does mean the claim sits at the boundary between physical inference and extrapolation. The deeper problem is not simply that something may exist beyond sight. Astronomy has always studied invisible things through their effects. The deeper problem is that regions beyond our causal horizon may produce no effect here at all. No gravitational pull can cross the boundary faster than light. No collision can send evidence backward through the expanding separation. No future telescope can be placed outside our causal region and transmit its findings home. If such regions exist, their independence is not caused by distance alone. It is enforced by the geometry of the universe. We may be part of a continuous reality whose overwhelming majority cannot interact with us now, could not have influenced us in the past, and will never enter our future. That would make the observable universe more than a limited sample. It would make it a sealed sample. And once the sample is sealed, there may be no observation capable of telling us whether the unseen whole is merely larger, fundamentally different, or without any total boundary at all. There is a temptation to treat this as a temporary failure. Perhaps the equations are incomplete. Perhaps the instruments are not sensitive enough. Perhaps a future theory will turn the hidden universe into a solvable problem. That may happen for some questions. It will not happen for all of them. A better theory can reveal consequences we have not yet noticed. It can connect measurements that once appeared unrelated. It can show that only one larger structure is compatible with the inside our horizon. But even a perfect theory cannot create observations where no causal connection exists. This separates two very different kinds of uncertainty. The first comes from ignorance. We do not yet know enough. The second comes from underdetermination. More than one possible universe may produce exactly the same observable evidence. If two models make identical predictions for every signal that can ever reach us, then no experiment inside our region can distinguish between them. One may describe a universe that continues forever. Another may close on itself far beyond the horizon. A third may place our visible domain inside a much larger structure with conditions that vary elsewhere. If each model agrees on everything we measure, the difference between them remains real in the mathematics and inaccessible in the evidence. That is not a weakness unique to cosmology. Science often compares explanations that initially fit the same data. New experiments usually force them apart. The cosmic horizon creates the possibility that some experiments can never be performed. This is why the total size of the universe is not simply an unknown number waiting for a more precise instrument. There may be no observation capable of assigning that number. Curvature measurements can set limits. Searches for repeated patterns can exclude compact geometries below certain scales. Studies of the microwave background can test whether the visible region behaves as though it came from a larger, nearly uniform domain. Each result narrows the possibilities. None requires the remaining possibilities to collapse into one answer. Suppose future measurements show that spatial curvature is indistinguishable from zero to extraordinary precision. The inference that the universe is extremely large would become stronger. Yet an infinite flat universe, a finite flat universe with a vast repeating topology, could remain observationally similar across our horizon. Now suppose no repeating pattern is ever found. that would show only that any repetition occurs beyond the observable scale, or that the topology does not produce a simple detectable pattern. Absence can rule out what should have appeared. It cannot always identify what remains. The same problem affects attempts to determine whether our observable patch is typical. Cosmologists describe the large-scale universe statistically. Matter density, temperature fluctuations, galaxy distributions, and expansion history can all be measured across the region available to us. The results suggest broad uniformity when averaged over large enough scales, but the word typical requires comparison. To know that one sample is typical, we need some understanding of the larger population. In cosmology, the sample and the environment containing it may be nearly the same thing. We can compare different parts of the visible sky. We cannot compare our observable universe with another observable universe from an independent location. This creates an uncomfortable circularity. We assume that our patch belongs to a larger, statistically uniform cosmos because the patch itself appears uniform. The assumption succeeds in prediction, so it earns confidence. Yet its strongest version extends into regions where no confirming measurement can arrive. The alternative is not that Earth occupies a special center. The alternative is that the structure beyond our horizon may contain variations on scale arch to appear inside the region we can inspect. A small window can show a smooth section of a wall without revealing whether the building continues, curves, changes material, or ends just beyond sight. The analogy breaks at one critical point. We can step outside a room and inspect the wall. We cannot step outside the observable universe. Some theories try to recover information about the larger whole from conditions at the beginning. If the early universe emerged from a specific quantum state, or if inflation followed a particular potential, then the unseen regions might be constrained by the same physics that shaped ours. But this moves the uncertainty backward rather than removing it. We do not yet have a complete tested theory of the earliest moments. General relativity describes gravity and cosmic expansion with remarkable success, while quantum theory governs matter and interactions at small scales. In the conditions near the beginning, both should matter. Their full reconciliation remains unresolved. The part of cosmic history most likely to determine the size and structure of the whole is also the part where our current theories are least complete. Even the phrase beginning may be misleading. The hot, dense early state described by standard cosmology does not automatically establish an absolute beginning of existence. It identifies an early phase from which the observable universe evolved. Whether something preceded inflation, caused it, replaced it, or makes the question of before physically meaningless depends on theories that are not yet settled. So the hidden exterior and the hidden past may be connected. The universe beyond our horizon could carry information about conditions earlier than the oldest signals we receive. But if inflation erased or diluted that information within our patch, then the regions that might answer the question are precisely the regions we cannot observe. The evidence may exist. It may simply exist somewhere that can never affect us. This changes what it means to say that the universe has a structure. Ordinary objects can be mapped from outside. A planet has a shape that a distant observer can eventually see as a whole. A galaxy can be surveyed across its extent. Even a black hole reveals properties through the space-time and matter around it. The universe has no known external vantage point. Any description of the whole must be constructed from within one limited region of the object being described. There is no guarantee that the internal view uniquely determines the total form. A civilization could spend millions of years refining its cosmology. It could measure every accessible photon, every gravitational wave, every relic particle, and every statistical feature of large-scale structure. Its map of the observable universe might become almost complete. The map of everything could still remain ambiguous, not because the civilization failed, because the universe may contain facts that leave no trace inside its horizon. This is the point where the question stops being only astronomical. Science is built on the idea that reality can be constrained by evidence. The cosmic horizon does not overturn that idea. It defines where the evidence ends. Beyond that boundary, possible realities are not equally credible. Some fit established physics better than others. Some require unsupported assumptions. Some may be mathematically inconsistent. Reason can still rank them. But ranking is not the same as seeing. The whole universe may be finite or infinite. It may repeat, vary, or remain uniform beyond every reachable distance. It may be one connected domain, or part of a structure for which the word universe is no longer precise enough. We can build models of each possibility. What we may never be able to build is the experiment that tells us which model describes the regions that cannot answer back. The safest response is to limit the claim. We can speak confidently about the observable universe. We can describe its expansion, map its large-scale structure, estimate its age, and reconstruct much of its thermal history. We can test whether the same physical laws operate across billions of light years. Within that domain, the evidence is remarkably consistent. Light from distant galaxies carries the same atomic signatures measured in laboratories on Earth. Gravity shapes stars, clusters, and cosmic structure in ways that agree with the same underlying framework. The microwave background follows a pattern that can be compared with models of matter, radiation, and expansion. Nothing we observe requires the laws of physics to change from one side of the visible universe to the other. But consistency across the observable universe is not proof of consistency everywhere. There is a difference between saying that the same laws work throughout every region we can examine, and saying that the same laws govern all possible reality. The first is an empirical result. The second is an extrapolation. That extrapolation may be correct. It may be the most economical assumption available. Science depends on extending tested principles beyond the exact place and moment where they were measured. Without that step, prediction would become impossible. Yet the cosmic scale makes the extension unusually large. A physical constant could remain unchanged across 93 billion light-years of observable diameter and still differ beyond our horizon. A larger region could share our geometry, while another domain settles into a different state. The laws may be universal, or our visible cosmos may occupy one stable outcome among many. Current evidence cannot decide between every version of those possibilities. This is where the word multiverse often enters too early. It can make the problem sound more settled than it is. There is no direct observation of another universe. There is no confirmed signal from a separate domain with different laws. There is no image of a boundary between cosmic regions. What exists are theories in which a larger reality emerges naturally from the mathematics. Some models of inflation allow expansion to continue in distant regions after it ends in ours. Different domains could then develop independently. In some versions, conditions may vary between them. In others, the same broad physics may repeat across an immense structure. These ideas are not equivalent, and none should be treated as a measured extension of the sky. Their scientific value depends on whether the underlying theory explains what we observe, avoids internal contradiction, and produces consequences that can be tested here. A hidden region does not become scientific evidence merely because a theory permits it. But the opposite mistake is also possible. An inaccessible region does not become unreal merely because it cannot be observed from Earth. Reality is not required to fit inside our methods. The uncomfortable balance is that science must refuse certainty without pretending that untestable possibilities all deserve equal weight. Some larger universe models are strongly motivated by known physics. Others are speculative additions. Some solve real cosmological problems. Others move the unanswered question into a place no observation can reach. The horizon forces discipline. It does not tell us to stop reasoning. It tells us where reasoning changes character. Inside the observable universe, measurements can overturn expectations. Beyond it, arguments rely increasingly on simplicity, consistency, and the behavior of theories within the region we can test. That shift is subtle, but it matters. A model may describe the visible cosmos with extraordinary accuracy while remaining silent about the total size of space. Another may explain why our region appears flat and uniform while leaving the extent of inflation unconstrained. A third may predict many domains, but offer no clear method for distinguishing that prediction from a universe containing only one. The same successful evidence can support more than one larger picture. For human beings, this is not merely an abstract problem about distant geometry. Every statement we make about existence is made from inside one causal patch. The matter in our bodies came from processes within that patch. Every instrument we have built is confined to it. Every signal we have received belongs to its history. Even the concepts used to imagine what lies beyond were formed by brains that evolved inside one small galaxy, around one ordinary star. That does not invalidate cosmology. It makes its achievement more severe. We have reconstructed an ancient expansion, detected relic radiation, measured the curvature of space, and inferred events that occurred long before stars existed. The horizon has not prevented knowledge. It has revealed the difference between knowledge and total access. The distinction becomes sharper when we ask whether the entire universe even has a measurable age, in the same sense as our observable history. The age of roughly 13.8 billion years refers to the time elapsed since the hot, dense early phase described by the standard cosmological model. It does not automatically answer whether space-time began then, whether inflation preceded that phase, or whether a larger structure existed in some earlier form. The clock we measure may date the history of our accessible cosmic region. It may not date all reality. The same caution applies to size. The observable universe has a finite radius because light has traveled for a finite time through expanding space. That measurement says nothing by itself about whether total space is finite. A finite observation does not imply a finite object. Standing inside fog, a person may see 100 meters in every direction. The visible circle has a clear size. The landscape does not inherit that boundary. The cosmic case is harsher because the fog cannot be dispersed. There may be no higher mountain from which the full terrain becomes visible, and unlike ordinary fog, the horizon does not simply hide objects. It separates events from us. Some regions may never have influenced our history. Others may once have been connected to the matter that became our observable universe, then been driven away by expansion until no later information could cross the gap. The whole may contain a shared origin without a shared future. That possibility transforms the meaning of cosmic unity. We speak of the universe as one thing because our theories describe one space-time and one connected history. But connection may exist only in the equations, not in any exchange of information available now. Two regions can belong to the same mathematical structure while remaining forever absent from each other's evidence. If so, the universe is not merely larger than we can see. It is larger than any observer inside it could assemble into a single observation. Every civilization would inherit its own horizon. Each would reconstruct a local cosmic history. Each might infer a larger whole. None could step outside its causal region to compare the inference with the complete object. There may be no perspective from which the entire universe is visible at once. Not now. Possibly not anywhere. The question beyond the horizon is therefore no longer only about what exists there. It is about whether the idea of the whole describes something that any observer could ever know as a whole. There is one final assumption hidden inside the question. When we ask what lies beyond the observable universe, we imagine that somewhere there is a complete inventory of reality. Every galaxy counted, every region mapped, every boundary known. Physics gives us no such vantage point. Every observer is embedded in space-time, receiving information along a limited history of light and causation. There is no platform outside the universe from which the entire structure can be inspected. There may not even be a single observer-independent meaning of everything that exists now in the ordinary sense. Relativity allows different observers to divide events into space and time differently, while cosmology gives us a useful common clock because the large-scale universe appears so uniform. The whole universe may therefore be more than unseen. It may be unavailable to any possible point of view. Consider two civilizations separated by enough expanding space. Each may build telescopes, measure relic radiation, and reconstruct its cosmic history. Their observable domains could overlap partly, or perhaps not at all. Each could infer that a larger reality continues beyond its horizon. Neither could compare maps. There would be no final observer waiting between them, able to combine the records. The separation would be causal. That possibility limits one of our oldest instincts, the belief that anything real must become knowable if intelligence survives long enough. Many things probably will. Better detectors may reveal relic particles we have not yet measured. Gravitational waves may carry information from earlier periods than ordinary light can reach. New theories may connect inflation, quantum physics, and gravity in ways that sharply reduce the range of possible cosmic histories. But every successful discovery will still arrive from inside our causal patch. No detector can receive a signal from a region that never shares a causal path with it. No equation can turn the absence of all possible contact into a measurement. A theory can tell us what likely lies beyond the horizon, perhaps what must lie there under certain assumptions. The assumptions will still be doing work that observation cannot finish. This does not make cosmology a failure. From one galaxy in one observable region, we have recovered a coherent history stretching back to a hot, dense early phase. We have measured the expansion of space, the composition of the cosmos, and the small early variations from which later structure formed. We have found that the same physical rules operate across distances no human being can cross. The achievement remains real, even if it never becomes complete. Science does not need access to all existence before it can produce reliable knowledge. It needs models that survive contact with evidence. The difficulty is that the strongest models may eventually lead to a boundary, where several larger realities remain compatible with everything the evidence can say. At that point, uncertainty is no longer an empty space waiting to be filled. It becomes part of the structure of the problem. The universe could be finite and closed, on scales far beyond our horizon. It could be spatially infinite. It could be one immense inflationary region, or one domain among many. The same laws may continue everywhere, or our accessible region may represent only one outcome. Those possibly do not deserve equal confidence. Some are better motivated. Some introduce more assumptions. Some may fail as theories improve. Yet the final elimination may never occur. There may always remain more than one account of the whole universe, consistent with every observation available inside it. That would mean reality contains facts that are true without being recoverable. A region may exist with galaxies, matter, and a history entirely separate from ours, while leaving no detectable mark here. Its existence would not depend on our ability to verify it. Its details could be definite, even if no observer anywhere can compare them with our own. Human knowledge developed in environments where hidden things could usually be approached. A valley could be crossed. An ocean could be sailed. A dark part of the sky could be studied with a larger instrument. The cosmic horizon is different. It does not challenge distance with greater effort. It defines which events can belong to our evidence at all. The boundary around the observable universe will continue to change. Some ancient signals will arrive for the first time. Others will stretch and fade. Distant regions will slip beyond any possible future exchange. The archive will grow in one sense while closing in another. Humanity exists during a period when that archive is unusually rich. We can still see galaxies beyond our gravitational neighborhood. We can still detect radiation from the early cosmos. We can still compare traces of expansion and structure. But even now, while the sky is generous, it is not complete. The observable universe is centered on our location only because information reaches us from every direction. Move to another galaxy and the boundary changes. Wait long enough and it changes again. There is no single visible cosmos shared in full by every observer. What we call the universe is partly a physical object and partly an inference assembled from one position within it. The inference may be correct. It may also be permanently incomplete. The boundary we began with was never the edge of reality. It was the edge of received information. Beyond it, existence may continue for distances that make the observable universe look negligible, or it may close in a form too large for us to recognize. We may one day understand the equations well enough to know which possibility is more likely. We may never know which one is true. So the final question is not simply what exists beyond the cosmic horizon. It is whether reality was ever required to place all of itself within reach of an observer. The observable universe is not the whole universe, and the whole universe may be something no one, anywhere, can ever see as a whole.